Chapter 1, Section 5, Diffusion Potentials and Equilibrium Potentials. Ion channels. Ion channels are integral membrane proteins that, when open, permit the passage of certain ions. Thus, ion channels are selective and allow ions with specific characteristics to move through them. This selectivity is based on both the size of the channel and the charges lining it. For example, channels lined with negative charges typically permit the passage of cations, but exclude anions. Channels lined with positive charges permit the passage of anions, but exclude cations. Channels also discriminate on the basis of size. For example, cation-selective channels that lined with negative charges might permit the passage of sodium, but exclude potassium. Other cation-selective channels, for example, the nicotinic receptor on the motor end plate, might have less selectivity and permit the passage of several different small cations. Ion channels are controlled by gates, and depending on the position of the gates, the channels may be open or closed. When a channel is open, the ions for which it is selective can flow through it, down the existing electrochemical gradient. When the channel is closed, the ions cannot flow through it, no matter what the size of the electrochemical gradient. The conductance of a channel depends on the probability that it is open. The higher the probability that the channel is open, the higher its conductance or permeability. Two types of gates control the opening and closing of ion channels. Voltage-gated ion channels open and close in response to changes in membrane potential. Ligand-gated channels open and close in response to the binding of ligands, such as hormones, neurotransmitters, or second messengers. Voltage-gated ion channels have gates that are controlled by changes in membrane potential or voltage. For example, the activation gate on the nerve sodium channel is opened by depolarization of the nerve cell membrane. Opening of this channel is responsible for the upstroke of the action potential. Interestingly, another gate on the sodium channel, an inactivation gate, is closed by depolarization. Because the activation gate responds more rapidly to depolarization than the inactivation gate, the sodium channel first opens, then closes. This difference in response times of the two gates accounts for the shape and the time course of the action potential. Ligand-gated channels have gates that are controlled by hormones, neurotransmitters, and second messengers. For example, the nicotinic cholinergic receptor on the motor end plate is actually an ion channel that opens when acetylcholine, or ACH, binds to it. When open, it is permeable to sodium and potassium ions. Diffusion potentials. A diffusion potential is the potential difference generated across a membrane when a charged solute, an ion, diffuses down its concentration gradient. Therefore, a diffusion potential is caused by diffusion of ions. It follows then that a diffusion potential can be generated only if the membrane is permeable to that ion. Further, if the membrane is not permeable to the ion, no diffusion potential will be generated, no matter how large a concentration gradient is present. The magnitude of a diffusion potential, measured in millivolts, depends on the size of the concentration gradient, where the concentration gradient is the driving force. The sign of the diffusion potential depends on the charge of the diffusing ion. Finally, as noted, diffusion potentials are created by the movement of only a few ions, and they do not cause changes in the concentrations of ions in bulk solution. The concept of equilibrium potential is simply an extension of the concept of diffusion potential. If there is a concentration difference for an ion across a membrane, and the membrane is permeable to that ion, a potential difference, the diffusion potential, is created. Eventually, net diffusion of the ion slows and then stops because of that potential difference. In other words, if a cation diffuses down its concentration gradient, it carries a positive charge across the membrane, which will retard and eventually stop further diffusion of the cation. If an anion diffuses down its concentration gradient, it carries a negative charge, which will retard and then stop further diffusion of the anion. Equilibrium potentials. The equilibrium potential is a diffusion potential that exactly balances or opposes the tendency for diffusion down the concentration gradient. At electrochemical equilibrium, the chemical and electrical driving forces acting on an ion are equal and opposite, and no further net diffusion occurs. The following examples of a diffusing cation and a diffusing anion illustrate the concepts of equilibrium potential and electrochemical equilibrium. Figure 1-11, also shown on page 16 of your book, shows two solutes separated by a theoretical membrane that is permeable to sodium but not to chloride. The sodium chloride concentration is higher in solution 1 than in solution 2. The permeant ion, sodium, will diffuse down its concentration gradient from solution 1 to solution 2, but the impermeant ion, chloride, will not accompany it. As a result of the net movement of positive charge to solution 2, a sodium diffusion potential develops, and solution 2 becomes positive with respect to solution 1. The positivity in solution 2 opposes further diffusion of sodium, and eventually it is large enough to prevent further net diffusion. The potential difference that exactly balances the tendency of sodium to diffuse down its concentration gradient is the sodium equilibrium potential. When the chemical and electrical driving forces on sodium are equal and opposite, sodium is said to be at electrochemical equilibrium. This diffusion of a few sodium ions, sufficient to create the diffusion potential, does not produce any change in sodium concentration in the bulk solutions. Figure 1-12, also shown on page 16 of your book, shows the same pair of solutions as in Figure 1-11. However, in Figure 1-12, the theoretical membrane is permeable to chloride rather than to sodium. Chloride will diffuse from solution 1 to solution 2 down its concentration gradient, but sodium will not accompany it. A diffusion potential will be established, and solution 2 will become negative relative to solution 1. The potential difference that exactly balances the tendency of chloride to diffuse down its concentration gradient is the chloride equilibrium potential. When the chemical and electrical driving forces on chloride are equal and opposite, then chloride is at electrochemical equilibrium. Again, diffusion of these few chloride ions will not change the chloride concentration in bulk solutions. Nernst equation. The Nernst equation is used to calculate the equilibrium potential for an ion at a given concentration difference across a membrane, assuming that the membrane is permeable to that ion. By definition, the equilibrium potential is calculated for one ion at a time. Thus, E is equal to negative 2.3 times R, which is the gas constant, times T, absolute temperature, over Z, which is the charge in an ion, for example, +1 for sodium, +2 for calcium, -1 for chloride, times log base 10 of the ratio of the intracellular concentration over the extracellular concentration. In words, the Nernst equation converts a concentration difference for an ion into a voltage. This conversion is accompanied by the various constants. R is the gas constant, T is absolute temperature, and F is Faraday's constant. Multiplying by 2.3 converts the natural log to log base 10. By convention, membrane potential is expressed as the intracellular potential relative to the extracellular potential. Hence, a transmembrane potential difference of negative 70 millivolts means 70 millivolts cell interior negative. Typical Nernst potentials are as follows. The Nernst potential for sodium is positive 65 millivolts, For calcium, positive 120 millivolts. For potassium, negative 85 millivolts. For chloride, negative 90 millivolts. It is useful to keep these values in mind when considering the concepts of resting membrane potential and action potentials. Sample problem. If the intracellular calcium concentration is 10 to the negative 7th moles per liter, and the extracellular calcium concentration is 2 times 10 to the negative 3rd moles per liter, at what potential difference across the cell membrane will calcium be at electrochemical equilibrium? Assume that 2.3 times R times T over F is 60 millivolts at body temperature, which is 37 degrees Celsius. Solution. Another way of posing the question is to ask what the membrane potential will be given this concentration gradient across the membrane if calcium is the only permeant ion. Remember, calcium is a divalent, so Z is plus 2. Thus, the Nernst equation, or the Nernst potential for calcium, is negative 60 millivolts over Z times log base 10 of the inner concentration over the outer concentration, which is negative 60 millivolts over 2 times the log base 10 of 10 to the negative 7th molar over 2 times 10 to the negative 3rd molar, which is equal to negative 30 times log base 10 of 5 times 10 to the negative 5th molar, which is negative 30 times 4.3, or positive 129 millivolts. Because this is a log function, it is not necessary to remember which concentration goes in the numerator. Simply complete the calculation either way to arrive at 129 millivolts and determine the correct sign with an intuitive approach. The intuitive approach depends on the knowledge that because calcium is much higher in the ECF than ICF, calcium will tend to diffuse down this concentration gradient from ECF into ICF, making the inside of the cell positive. Thus, calcium will be at electrochemical equilibrium when the membrane potential is positive 129 millivolts, cell interior positive. Be aware that the equilibrium potential has been calculated at a given concentration gradient for calcium ions. With a different concentration gradient, the calculated equilibrium potential would